Now let's take a look at solid edge ST3 simulation. One of the first things that I want to point out is that we have now the ability in ST3 to simplify our models and utilize them in our analysis through simulation. So what I'm going to do is I'm going to go ahead and in-place activate into this spindle, and on quick bar I'm just going to turn off the background components temporarily so you can kind of see what I'm focusing in on. And what I want to do is I want to simplify this model. So I'm going to go ahead and turn on the simplified mode, go over to my modify, and in this case I'm going to remove some faces that I don't want to include in the analysis. Now in the long run, what's this do for us? It allows us to simplify the model and shorten up the time to run the analysis by removing faces and features that don't need to be included in the analysis. Again, something that we've added in ST3. So when I'm done with that, we can go back to our top level or our subassembly, and you'll see that the part still has the design features in it, but if I select that particular part and choose to use the simplified part, when I run the analysis now, it will just use the simplified model. So again, simplification becomes very simple and easy in synchronous technology. Now we want to go ahead and start the simulation process. And the first thing we do when we create a study is we define the geometry. And the easiest way to do that is to select the geometry, right mouse button click to accept it. Once the geometry has been defined in an assembly, the commands become active. Now obviously we can reduce the need for physical prototypes by providing a wider range of simulations. In an ST3 we've also included torque and bearing loads, and as far as constraints we've included user defined, giving our users a wider variety of tools to define loads and constraints. For this particular model we're going to define a force on the blade. So if this blade is spinning at a high rate and it hits a rock, are the parts going to respond? And that's what we're actually looking at here. So we'll go ahead and apply a force to our blade. The next thing that I'm going to do is I'm going to go ahead and fix this plate. Now this plate basically represents the deck of the mower, and it's just a simplified piece of that deck. So we'll go ahead and define those relationships. Now we need to tell the system how these parts are connected to each other. Under the connectors collection, you'll notice we have an automatic and a manual method. Let's use the automatic. It's the easiest. And we can define the parts, in this case these three parts, and we're going to tell the system that we're going to glue these together. Now what it does is it brings up the results dialog, and we'll click on the create connectors, and you'll notice that it actually creates those connectors for us. What I'm going to do is go ahead and turn that information off just to kind of clean up the view a little bit. And the next thing that we want to do is we want to tell the system how the spindle and the deck are connected. And for that case, we've added bolted connections in ST3. Now I can obviously go around and select each one of the holes, but we also have a method to select them all on a plane. By selecting one hole, it'll go across that plane and find all the holes on that plane, and you notice that it extracts all of the pertinent information from the holes: the bolt diameter, shaft diameter, nut diameter, and then of course the pre-stress force. We also want to go ahead and turn on the spider, which means it's going to make a connection between this bottom face of the spindle and the top face of the deck, and we'll put them in the same collector. And I'm also going to change this pre-stress value to 100. Now by doing that, it's going to go ahead and create the bolted connection for all four of those holes. Once that's done, we're ready to mesh the part. So we can go ahead and click on the mesh command. It's going to mesh the model. Obviously we have tools to define meshes for edge, surfaces, or bodies. So we can change the mesh size for each one of these bodies, edges, or surfaces at will. And then when that's done, we can run the solve and get our results. And you'll notice the feedback is very quick. Now looking at the results, you can see that the shaft on the spindle is taking quite a hit. There's a lot of stress on that shaft, and we want to be a little bit more specific. We can use our probe tool turn on the show displacement, and we can actually extract that information and actually see what the deformation value is, and the node and the node information and the value of that. And we can place that. And you'll notice when we place it, it adds it to this probe table. This information can be easily copied into an Excel spreadsheet to pass along to this pertinent information to somebody that's interested in the study that we're doing. But we can see that we've got some work to do on this shaft. So I'm going to close the simulation, and I'm going to go back and I want to make a change. Now that's one of the other cool things about Solid Edge with synchronous technology. To make design refinements is faster and easier. All we have to do is simply edit the model. In this case, we're going to in place activate. I'm going to go back to the synchronous part of this model, and what I want to do is I'm going to create a live section. Now I'll show you what a live section is going to do for us. It actually creates a section right in the middle of that part, or wherever the plane is that we select is placed. And then by selecting the edge of that live selection on this diameter, it shows me what that diameter is. So I can easily change this value by scrolling my mouse, or I can key in a specific accurate value. I want it to be 60 millimeters diameter. I want to use my steering wheel to simply pull this down a little bit to make it stronger. I'm going to bring it down about 40 millimeters. And then finally, the diameter that had all the stress, it's only 25 millimeters in diameter. So I'm going to fatten it up by taking it up and maybe key in a value of 40. So you can either scroll the value or you can key a specific value in. When that's done, we can go back to our subassembly, and you'll notice that even though we're still using the simplified version, the diameters have all been updated. So what we want to do is go take a look at our second study. Now in this particular study, we've already defined the loads and constraints. We just need to add the new model to this particular study. And once that's done, we can take a look at the mesh that was created. You'll notice it replicates that geometry that was changed in size. And of course, when that's done, we can take a look at the results. And you'll notice once I turn off the loads, the constraints, and the connections, you'll notice that there's a lot less stress on that shaft because we've beefed it up. Now in ST3, we've also added another capability. Of course, there's more stress on the blade, and blades are cheaper to replace than an actual spindle component. But we can come over, and if we want to expand the mesh portion, we can actually turn off some of these external components so that we can take a look at the mesh on internal components. Again, this is something new that we've added in ST3, and I think that our customers will find that quite valuable. But in this case, let's go ahead and turn those parts back on. And then some other capabilities that we have. Now you'll notice that we are in the results section, and there's the home tab. We have the display tab if you want to change any of the display of your results, or even the color bar. We have a color bar tab where you can change to user defined scale if you want to change the scale, turn on and off the minimum and maximum markers, things of that nature. But what I think is pretty cool is the ability to come over and change the deformation. Now we're looking at the actual deformation, but if we want to exaggerate that maybe to kind of get an idea of what could happen, we can change it to the percentage option, and in this case it's set to 10%. And you can notice that the results are exaggerated a little bit, but we can also run the animation on this, and you'll notice how it actually shows you how the parts will actually move in an exaggerated form, of course. Finally, I think it's important to be able to output the information, a final report of this analysis. Again, this is an engineer who might not be a top-level analysis person, but he wants to be able to analyze his parts quickly and easily, and that's why we provide Solid Edge ST3 simulation. We want him to also be able to create a report very quickly, so we're going to go ahead and do that. And you'll notice I added our Solid Edge Velocity Series logo, which is in in this file. Again, you can key in your company name, the report title, the author, any of the pertinent information, but more importantly, we can output to HTML or even a Word document. So let's go ahead and hit the Create Report. It's going to take a nice shot of each one of the results that we have, whether it's deformation or stress, and then it's going to actually create this Word document that we'll just bring to the front here. And you'll notice it takes in and shows us our image. It could be your company logo. And then we can come down and scroll through all of the information created in the report. We also have active links here. So if we go right to the results, it shows us what the results look like. Stress results, factor of safety results, von Mises stress, whatever you're looking for, that information is in the report. So again, Solid Edge ST3 simulation provides our users with a lot of capabilities. First of all, reducing the need for physical prototypes through a wider range of simulations. By being able to simplify our models is huge because it removes the unnecessary geometry and allows us to get faster results. And then of course, making design changes just doesn't get any faster or easier than what we can do with synchronous technology.